We're really excited about today's episode. We've got some meteorology going on. My name is Pallas. I'm a librarian, and we have our special guest today, Elizabeth Smith. Yay! Don't everyone clap at once. Wow. Today's sponsors are Project 3810. They have an amazing venue here. It's wonderful. You should definitely check them out. And so let's start off today's science episode by having Elizabeth tell us a little bit about herself.
Sure. So my name is Elizabeth Smith, and I'm a very recent PhD grad from the University of Oklahoma, and my degree is in meteorology. So I study the weather, and you may or may not know that Oklahoma is maybe one of the best places in the world to study the weather. So I currently work at the Cooperative Institute for Mesoscale Meteorological Studies and the National Severe Storms Laboratory in Norman. So a big part of my job is working with some of the best people in the world that study our weather. So I'm not the person on the TV, but I go into work every day to try to understand all this crazy weather that happens here in Oklahoma and elsewhere around the world.
That's really, really cool. So the National Weather Service is located in Norman, right?
So I work in the National Weather Center, which is one big building.
Okay.
And inside that building, there is the University of Oklahoma School of Meteorology. There's the Cooperative Institute, who I'm employed by, the National Weather Service, who's responsible for your forecasts and warnings. And then we also have the National Severe Storms Laboratory, which is the federal research partner, the Storm Prediction Center, which is responsible for the entire country's watches. And then we have some more partners like the Oklahoma Climatological Survey, some other folks in the building too.
So there's a lot of
stuff going on.
That's awesome. So what are some misconceptions people might have about meteorology or being a meteorologist or in the field?
So the most common one that I get is, well, when will I see you on TV? So most people, when they think about meteorology, they think about the weatherman or the weatherwoman you see on the news every day, and that has never been and probably will never be part of my job. So I'm a scientist. I do science every day. So I ask questions, I try to answer those questions, but I do that with respect to the weather. So I'm not a TV weather person.
So what would your typical day be like?
So it looks like probably what most scientists' jobs look like in some way or another. So I get up in the morning and I go to work, and some days are different than others. So most of my days I spend a lot of time with the computer. So I spend a lot of time coding, working with big data, looking at observations, looking at model output, kind of these things, a lot of this. But I'm really fortunate because another really cool part of my job is I actually get to go out and do the thing. So I go out every spring and sometimes different times of the year, and I observe the weather. So we have really important instruments that we take out, so I get to go do that. So I get to get out of my chair every now and then and do some science outside.
So when you say out, do you mean like in the field, like literally you're outside in the weather as it's happening?
Correct.
Okay, so like Twister or?
So Twister, no, yes, but no. Twister is false, but the real version of that, yes. So I actually just got back from a big field campaign called TORUS, which stands for Targeted Observations by Radar and UAS of supercells. Something you'll learn about us is we're really into acronyms. So TORUS was a big field campaign. I was out 5 weeks, completely nomadic, so day to day we were somewhere new, following supercell thunderstorms and tornadoes. So we were taking observations in the vicinity of strong, severe thunderstorms and the tornadoes that may or may not occur with them.
That's so cool, yeah. And very interesting. What was the most interesting thing you saw while you were out in the field this spring?
Weather-wise, I would say the most interesting thing I was fortunate enough to see, we set up on a isolated storm in southern Kansas, and it got to sit there for a long time. So when these storms sit there for a long time, instead of looking just like yucky gray blobs, they get these really amazing, beautiful shapes. And so they're round and they have all these layers. It's like stacks of pancakes. And so we're looking at this stack of pancakes, and it's beautiful, right? It's beautiful. And then an anticyclonic tornado formed. And most people probably won't care what that means, but what that means is it turns the other way than most tornadoes that we observe. So I got to see, both with my instruments and with my eyes, a tornado that is very, very non-typical. Oh. And it was out in the middle of a field, not hurting anyone, which also a really big bonus. So, and when they're out in the middle of the field not hurting anybody, they suck up a lot of dirt, so they get really pretty.
That's so interesting. Yeah. So I didn't realize that most tornadoes spin a specific direction, and that is so cool. Huh. So what would you say you are most proud of in your accomplishments so far?
Getting the PhD. Yeah.
A long process?
Yes, a long process. So I went to school for 9 years, 8.5 years. I went to college for 8.5 years, but now people have to call me doctor. Right?
Yay!
So that's pretty cool. But it's really neat to actually be able to say that I finished that. It's something on paper. You know, I've done lots of things scientifically, and I care about them, but sometimes it's hard to convey to other people what those accomplishments are. But this thing is a big, huge piece of paper, and I have a floppy hat and all this cool stuff. So it's pretty cool.
That is so awesome.
Yeah.
Dr. Smith.
Thank you.
Yes. So what made you super interested in your field? What got you into the field of meteorology?
So meteorology is a funny field. So not all of us, but a lot of us kind of discovered our passion when we were pretty young. And for some people, that something happens to them. You know, maybe they were impacted by a weather event or something. For me, it's a little bit different. So I was apparently faced with the Wizard of Oz, much too young, I don't know. And I was really, really terrified of the Wizard of Oz. And I'm from the tornado in particular, not all the other scary stuff that happens in there. And I'm from West Virginia, so a different part of the country. It's mountainous there, there's a lot of terrain, and I live on a river at home, and so we didn't have a basement or a shelter or anything like this. And I was, probably 6 or 7, and I was just horrified. I couldn't sleep at night because I thought that the tornado was going to come for us and we didn't have a shelter. And so I was an annoying child about that, apparently. And eventually, friends of my family started buying me weather books. Oh. So I have all these weather books. I should have brought them. I have all these weather books that are copyrighted like 1996, 1997, and they're just like hard cardboard books with pictures of tornadoes and safety instructions and things like this, and it's been a long road since then.
Are you as fearful of tornadoes now as an adult?
No.
Okay.
No. So I think that for me, I'm a question asker. I was a really annoying kid that would say why a lot. Why? And so my way of coping with the fear was to figure out why. Why would this happen? Why would it happen? When would it happen? Those sorts of things. And so that is sort of also what ignited my scientific curiosity. So I don't study tornadoes actually at all. They're just happening in the area where I study things.
You went from West Virginia to Tornado Alley.
Yes. But I still get to ask those questions, and that's what keeps me from feeling fearful, is getting to ask questions and work through the scientific process of answering them.
That is so cool. So what do you like best about the field of meteorology? What do you get to do in your job that you just love?
So weather changes every day. Every single day. So I'm never trapped by having to do, the same experiment every day or the same tasks every day. And research gets monotonous. It definitely does. I'm a researcher, so I spend a lot of time sitting at the computer and something's not working, and that's hard. But at the end of every single day, I get to go outside and look at the clouds, and I know why they're there, and that's really cool.
That is really cool.
Really
and no
cool.
matter where you go, studying weather is important.
Yes.
And every single person needs to know and have that knowledge, so that's really, really awesome. So what are some challenges that you've had to deal with in your field so far?
So meteorology is a fairly young science, so really it's only been happening here in the US for 60 years as a true research science. So a lot of things are new. We're still kind of etching out our place in the world. Climate change is a big deal right now, and it should be. But a lot of times that gets looped in what we're doing. And I'm not a climate scientist, I'm a meteorologist. So a lot of times it's hard to really communicate with people either that I'm not a TV meteorologist, I'm doing research, I'm trying to solve problems, I'm trying to answer questions. And then on the other hand, I'm also not researching climate. So it's hard to kind of live in that middle space. Here in Oklahoma, it's actually a whole lot easier than almost anywhere else in the country, because here in Oklahoma, people care about the weather, and that's really important, and that's really what makes our job a lot easier, but that's not true a lot of places.
Man, that's crazy. So obviously you went to school for 8.5, 9 years. That's a long time.
Yes.
What all did you have to learn and study to get to your point, to get your doctorate?
So one of the big misconceptions I think about meteorology as a science or as something that you study is that we're essentially applied mathematicians. So I do a lot of math. Like I use math every day, and so I'm kind of getting to be old enough to be stodgy, I guess. And I hear these people talk about, I'll never use calculus. Well, I'll never use algebra. Why is that even in high school? And I use calculus every day, and it's kind of scary to think about. But so I studied a lot of math, and applied sciences, so physics, things like this. Some of the things that we had to study, particularly in the undergraduate level, are just the other earth sciences. So we want to be well-rounded scientists. We don't only want to focus on the sky. So I had to take a lot of classes in like geology and things like this. So those were unexpected. I thought when I first entered into college, I really thought that I would be spending a lot of time talking about the weather the first couple of years, but that's not actually true at all. A lot of time talking about math.
So did you like math growing up,
yes.
or did you, okay.
Yes.
So you didn't have to grow to like it?
No, but I mean, that's something that I think a lot of meteorology students have to face. There are a lot of people that really love the weather. There are a lot of people that go outside and they just love storms. They want to know about that, but they're scared of math. But the really beautiful thing about meteorology is it's applied math. And so, when the math gets hard and it's hard to understand, and why would I even care about this? Well, there's a reason. And so it kind of can carry you through some of the more undesirable parts of math. So,
right, so as opposed to just learning theory, you're applying it,
yes.
so it makes it a lot easier.
Yes, everything's really applied. Cool. And then you get to go outside and see it. So when I'm talking about going outside and seeing the stack of pancakes and that anticyclonic tornado, there are equations that tell us why that would happen. And that's really pretty awesome to understand the math and then go out there and watch it happen.
So you're studying the weather. Do you also study its effects on things in and around the storm? For example, migraines and barometric pressure changes. Like that's a...
So I don't, but at the National Weather Center I mentioned earlier, there are tons of different entities in that building and in the community, and so there are people doing lots of applied meteorology research. So there's a lot of work in eco-meteorology, so understanding the impacts on animals and migration. So wind is very, very important to migration patterns, and so if we can understand more about the wind, we can understand a lot more about how migration patterns and different ecosystems might be impacted. Severe and extreme weather obviously have large impacts on the entire biosphere, right? So flooding displaces tons of animals, tons of people, things like this. So there are studies across the gamut from animals to people to other sciences, chemistry, things happening in the atmosphere. So meteorology is a science that can really apply to almost any other science. It's pretty neat.
That's really cool.
Yeah.
So do you have any advice for anybody who might be interested in getting into the field of meteorology?
Stay curious, and I know that's really kind of abstract advice, but I think a lot of us that are more scientifically inclined, maybe we tend to think of things as first step 1, then step 2, then step 3, and everything's really structured. But in meteorology, you think that you understand why a supercell may be forming or may not be forming, but then the atmosphere tells you something else completely is happening, and we still don't know a lot. And that's humbling, but it also keeps you really, really excited about what you're doing every day. So stay curious, feed that curiosity, whatever makes you wonder why. Keep following that, because that's what gets you through.
Keep asking why.
Keep asking why.
It's okay. Be that annoying kid.
Yes.
Keep asking why. Always ask why. Why?
Yes.
It's so important.
Yes. That's actually
for everything.
I think the dedication of my dissertation, my PhD dissertation, is to 8-year-old me for asking why.
Aw, that's so great.
Yeah.
I love it. I'm a librarian, so I love it when people ask why. I ask why every day. That's so wonderful. So I know you brought a machine of some kind. I was curious as to what it is for.
I did. So let me sneak it in here. It's kind of heavy.
You got it?
Yeah.
Woo, I'm so excited. I don't know what it is.
So I talked a little bit about how a big part of my job is field science. So I actually leave the office every now and then and get to go out and observe the weather. And we don't observe the weather with our eyeballs. We do. That's the fun part. But for the science, we need to collect data. And so what this thing is a mini version or a model version of clamps. And before I even get into it, I need to throw out a big shout out to the folks over at the Tom Love Innovation Hub, at the Fab Lab in particular. They built this thing for us to scale from our model. They worked with us every step of the way, and it's really, really cool.
And what is CLAMPS?
So CLAMPS stands for, or in acronyms, Collaborative Lower Atmospheric Mobile Profiling System. Okay. So a lot of words. All that really means is what this thing does is it measures everything going on in the atmosphere from the top of the trailer up through the first maybe 5,000 feet.
Okay.
Okay, so temperature, wind, moisture, all that good stuff. And we do that in a few cool ways. I'm actually going to flip this switch so it lights up.
Yay, lights!
Lights, people like lights. So the trailer's big. It's big enough that I and 4 other people can stand inside of it. So I'm going to pop this little guy off. So it looks just like this. And so there's 3 things going on in here. There's this thing that comes up and down through the ceiling, and this thing called a LiDAR. It's my favorite part, so we'll come back to it for last. Then there's 2 other instruments on here. There's this one and this one. This is a microwave radiometer and an ARRI, and those are big fancy words. What they do is they work together to measure temperature and moisture up through the first few thousand feet. And when we're talking about something like a thunderstorm, it's really important to know in this lowest part of the atmosphere what the environment's like. What air is that thunderstorm sucking in? Why is that important? What would it change if it were drier? Do we still have a cloud? Those sorts of questions. This little guy, he just measures temperature. He's cute. So this thing is the LiDAR. So this is my absolute favorite part. So it goes up and down in the real trailer. It comes up through the roof and it shoots a laser out. It's not a visible laser, so no Austin Powers.
No light shows.
No light shows. But the invisible laser, it goes up and it hits all of the dust and the dirt and everything up there, stuff that's too small for you and I to see. And we measure the Doppler Shift of that stuff. So what that means is, you know, when a train goes by and it blows its horn and the sound changes when it passes you, it gets louder and then quieter. That's the Doppler effect. And what happens basically is the waves get smushed as the train comes towards you, the waves of sound, and then the train passes you and those sound waves get stretched out, so the sound changes. The same thing happens with these waves. So what we can measure is how quickly then the dust and the dirt and all that stuff up in the air is moving. And if we know how quickly it's moving, we know how fast the wind is blowing. So wind is very, very important in the environment of strong, severe thunderstorms. You know, how is the wind changing in that environment? What's important about the wind? Those are questions we don't have all the answers to yet, because this lowest part of the atmosphere is actually the hardest part to observe. So this system, clamps, the real one, is helping to answer a lot of those questions. So I was out in the field with not all of this, just the LiDAR part, and we were taking these wind observations right in the very near field of tornadic storms.
So, and that goes all the way up 5,000 feet. And that's the lowest part of the atmosphere.
It's the lowest part of the atmosphere. So the part that we live in, so that's called the boundary layer actually. So I'm a boundary layer scientist. When we talk about meteorology as a whole, we're talking about the whole column. So all the way up, you know, tens to thousands of feet. I mean, when your local weather person comes on TV and they're talking about the fronts and the jet stream and all that stuff, those are really large scale weather patterns. They're really important. What I'm studying is this tiny little layer where you and I live. And it's kind of funny that that's where you and I live, but that's not where the weather people talk about, right? But it's because it's really hard to observe, so that's where we're starting. So this is really cool stuff. This is state-of-the-art measurement stuff.
That is so cool.
This is really cool. And this thing is really cool.
So it's just a tiny model.
Yeah, and it's got like suspension on it.
What?
So eventually we hope to hook him up to a little RC truck so we can drive it around.
That's so cool.
Yeah.
Awesome. Well, thank you so much for sharing that. So you guys just go out in this little trailer, out in the middle of a storm, and you're like, cool, wind.
Yep. The problem with the trailer, is that it's a trailer. So, you know, if you're driving in the vicinity of severe thunderstorms, they're windy. So you don't want to topple it over.
Right,
But we're safe. We have plans to mitigate that risk.
That is so cool. Well, thank you so much for sharing. So I do have to ask, what sort of inspiration or words of wisdom keep you going?
I'm going to move this first before I answer that. That's a really good question. So it depends on the day, I would say. I think that the most important thing that I've learned coming through the graduate school process and now working full-time as a scientist is I have to inspire myself. That sounds really selfish, but I have to inspire myself to do it every day. And so every single day, instead of trying to focus on who's inspiring me or what's inspiring me to keep me going, I focus on where I was 10 years ago, 5 years ago, and how much I can push myself today to keep going and keep being one of these people doing this amazing thing. So I hope that answers your question.
Yeah, absolutely. Yeah. So you look back on things that you've done and you're saying, hey, I have gotten so far. Got your doctorate after 9 years of study. That's so exciting, but you still have so much ahead of you.
Yes, so absolutely.
Cool. So my last question is, have you ever made a hot air balloon?
I have not.
So would the hot air balloon be flying in your boundary layer?
Yes.
Yes? All right,
Yes.
cool. Well, we are going to make hot air balloons. So you have instructions on the back of your Yes Science card.
Yes.
And we are going to make it. So what is the first thing that we need to do?
Make 5 sheets of tissue paper, 1 square and 4 rectangles.
Okay, so we've got some scissors, we've got some tissue paper. We need 5 sheets of them.
Yeah.
All right, what colors do you want?
Oh, I'll make a red balloon.
Ooh, here you go.
I'll give you all the red if you want all the red.
I'm gonna go, ooh, purple. Let's go with purple. Oh, there's so many things on here. So, is it already a square or a rectangle, or do we literally have to cut every single
Oh,
thing?
I was gonna make a small one.
Oh, okay. I don't know. How big do they have to be? Does it say?
It doesn't say.
It just says, okay.
Well, I guess, yeah, if we're gonna use a blow dryer, maybe it does need to be bigger. Is this a square?
I think it's a rectangle.
It's a square.
It's a square?
It's a square.
Ah, this is why I'm not in science. Just kidding. Libraries of science.
Well, let's make the square half this size so we can make this the size of the rectangle.
Oh.
Because otherwise our rectangles have to be really long.
All right. So, half the size of this. I'm letting her do all of the measuring.
The seams do it for us. So look, square.
Yes, because there's 4 squares.
So I guess quarter size.
Technically 6, almost. Unless my size of tissue paper is different. Oh no, I don't think so. All right, so we've got squares. And then after that, we have to make rectangles.
Yes.
Which are just also kind of already created, right? Because we could just cut one in half. and
Yeah,
two
they have to be
rectangles.
the same dimension as the size of our third square.
Man, making things complicated.
But we
Oh,
only
and then we
have
have to
one
glue afterwards. We've got little rubber cement glue stuff.
Okay, do you need a square?
Hey, thanks.
Yeah.
How many squares do we need? 4, 5?
2 squares, 4 rectangles each, so 8 rectangles.
Oh.
There's one. Oh, we can just cut these in half.
That's what I said earlier.
Oh, you were right.
It works perfectly. I just have to cut. So, tissue paper and rubber cement make hot air balloons. I'm interested to see how this works.
Hot air balloons are actually a really good meteorology experiment.
Oh yeah?
Yeah, so when you think about why clouds form or why storms form or whatever you want to think about. If you're a storm person, that's fine. If you're not, just think of a happy puffy cloud. Something has to create the bubble for it to go up.
Okay.
So what happens is the sun comes out and it warms the surface of the earth, and that's happy. And once the surface of the earth gets warm enough, it starts to kind of bubble like a pot boiling, or you can think of a lava lamp. The lamp makes the oil hot. And once that little pocket of air gets hot enough, it's hotter than the air around it, just like our hot air balloon will be. And so it rises.
Okay.
Yeah, and so that air rises and eventually it gets high enough to where it can condense out its moisture and poof, you have a cloud. It's exactly how clouds form. It's almost exactly.
Have you been in a real hot air balloon?
I have been in a hot air balloon once and it was horrifying.
Oh yeah?
Yeah.
Tell me
was
about that
very
experience.
scary. Well, it never was untethered from the surface.
Oh.
But that was enough for me. It's just, it started to lift and it just feels very like old-fashioned science. I don't know. I didn't trust it. And the wicker basket starts to kind of bounce when you're no longer on the ground.
Oh.
Yeah, I just did not feel safe. So I squatted down and tried to stay low inside the basket until we made it back to the surface.
That sounds like something I would do.
Yeah, I was scared.
I can't even imagine, man. I've been in a helicopter. That was pretty terrifying.
That sounds scary too. Yeah. One of the coolest things I've ever gotten to do with my job is I got to fly in one of the big hurricane hunter planes through a thunderstorm. So that
How was
pretty
that?
cool. Not as scary as you'd think. I thought it was going to be really scary. It was only moderately scary.
Okay, so on a scale of scary to scary, how scary was scary?
Okay, so I have too many rectangles.
4?
I have 5, so I'll get
Okay.
rid of 1. Okay. So now I have 4 rectangles and a square.
I have 4 and a square. So now what? Glue together the long sides of each rectangle sheet to make a balloon shape.
Where does the square go? I guess on the top. I think we have to glue it. I think we are supposed to cut this out of a single sheet. Oh well, so we can glue this to the, like, right, so like this to make the cross shape, and then we can do that. We just have to add a step. Okay.
5 sheets of tissue paper.
Another
one
important
square
science
piece
task.
Or...
Solve your mistakes in real
Right?
time.
Let's see. All right, we've got more tissue paper. If we have to make 7, it's a.
I thought
like
it would be
little
a brush.
ball.
It's
Maybe
kind
that
of
is
cute.
a brush. Like a little fuzzy ball brush.
It's like a cotton ball.
The smell of rubber cement that you cannot smell through the camera, but you guys will smell shortly.
Tis strong. So we're doing this because this was the step that we messed up by cutting out the square instead of cutting this out of a single piece of tissue paper.
Okay.
So this is invisible step 1.5.
But when it says 5 sheets, like how does this become a balloon?
So we'll
that?
glue these together
Okay.
like this.
Ah.
Right? You see?
Right.
Okay.
But then we have to have like space.
I glued 2. Well, this is the top of the balloon.
Okay.
This will be the bottom of the balloon.
Okay. And it will be really cool.
Yeah.
Whether or not it floats. We'll see. We'll see.
Oh.
I always have so much confidence in my science experiment abilities. Woo! I got that one wet. Let's do it.
We're gonna glue our balloons together. We're not. I'm saying we might accidentally.
I'm trusting you as a PhD scientist to do amazing things.
It might be a mistake.
That's what they all say. Yay! Yay! It looks so cool. I need the scissors. Because I got my other ones wet. I guess unless, okay, if these don't work, I guess we have to try again to do like a weird,
Do it the right way.
to do it the right way.
Always try the wrong way first.
Right? Well, I mean, science, you don't get it right in the first experiment, right?
Never.
That's not gonna happen. So I guess another question I have is how many times do you have to do an experiment and get it to make the same results for it to become scientifically proven?
Well, depends on your science. So, meteorology, we like to call ourselves an exploratory science instead of an experimental science, which basically means we get to break the rules of the scientific method a little bit.
Okay.
But for us, 3, probably.
3?
3 times if you can produce it. 3 times, it's probably pretty good.
So what if you do 3 experiments and they're all right, so then you've proven it. If you do 30 times and only 3 times are right, have you proven it?
We've not proven it. We've proven some sort of, there's some other sensitivity in there.
Okay.
But we do need 30 years of data for a climate record.
Oh,
if that
it's
counts.
like a square.
Yeah.
See, I was expecting like a round. My brain could not compute.
Oh, I'm hogging the glue, I'm sorry.
Oh, you're fine. Your hot air balloon's likely to be much better than mine. Yay! So I wonder if we have to let the glue dry.
It's drying pretty fast.
Whee! Okay, now I have to do the fancy gluing thing that you just did. Do you want to
Yeah.
try yours out?
Oh, sure.
Let's try yours. Oh,
Are you gonna be my hot air source?
oh, maybe.
Oh.
Let me try again, but inside. All right. Oh!
I think you just blew it away.
I think so too. Wait, hold on. It says inflate your balloon, hot air from air dryer while having another person hold the balloon. Got it. Bag becomes buoyant as it lifts with hot air. When you feel the bag tugging, release it.
Settings
All right.
are on here. Let's do
That was the one.
all heat,
All heat.
low fan.
Okay, all heat, low fan.
Oh yeah, this is better.
Oh, and it went upside down again. Oh, nope.
Don't ride this hot air balloon.
Yeah, so that hot air balloon is not going to work. But
Let's see if yours is more airtight.
I highly doubt it. Let's see here. Anything that we can base off of your experiment that might make my experiment more or less efficient?
Yes, I think so. So one, I thought it was going to be a circle too, which was part of the problem. So I think that we can like only do half at a time. So I don't want to, okay, that's scissors. So let's lay it over on its side.
Ooh.
And then we can glue them together like this instead of trying to do it up in the air like I did.
There you go. I'm gonna let you do it.
Okay, here, hold this one.
Yes. So, if we made it a circle, do you think it would be better? Like if we added some little wings on the angle?
But then it gets heavier,
Oh.
right?
But would heavier be better? Because right now the issue is that it's going too high too fast.
True, and it loses its buoyancy too fast. Ooh, that was a science word, buoyancy.
As opposed to radiancy. So what would make this a successful experiment?
Well, if we could figure out, from a meteorological perspective, we'd want to figure out what the relationship is to how much it flies or doesn't fly to how hot the air has to be coming out of the blow dryer. So could we establish how much heat you need to make your balloon buoyant? So we'd need to have a controlled heat source. We need to be able to measure the heat, the thermostat, the temperature.
So you've been in a hot air balloon. How did they measure?
Large fire, I don't know. It was a large fire. That was the other part that was really scary. It was a large fire, like right by my head. I assume that based on all the funny things that the hot air balloon pilot had in front of him, that there must be some sort of computer that tracks how much fuel they're using.
Hot air balloons use computers?
Yeah, there was some little screen in there to let us know. Also to track other stuff so they don't crash it into other things, I guess. It's pretty high tech.
Yeah, I guess that's important.
For a balloon with a wicker basket.
Right? I wonder how they did it in the old days.
Cross their fingers.
Cross your fingers, hope to fly.
Oh.
Yep. Bad puns make the world go round. All right, I have strong beliefs in this hot air balloon. I kind of wish we had a cute little basket to attach to it.
And we can make mine a basket. It's very long. I feel like that might be part of our problem too.
Where? Oh, there it is. Let's see. We've got it on the highest heat. Just want to do one.
Okay, we're gonna let it get really warm this time.
Go away! Go away, hot air balloon.
All right, here's my next modification. We're gonna make
yay.
it shorter.
Okay, let's see. Let's see if shorter means better. It's like half.
Yeah.
Aww, look
Oh, that's a
at
hat. Okay.
If I wear this hat, does it mean that I have hot hair? Woo! Go away. Well, that was fun.
That was fun.
I'm not quite sure how it was supposed to go. I wish, at the very bottom it says, note, there are many ways to do this, including using plastic bags and candles. Have fun experimenting with your own methods. Which I feel like we kind of did.
With adult supervision.
Oh, it doesn't add
It
that.
doesn't say that.
I'm going to write that in. With adult supervision. As an adult scientist, you are my adult supervision in this experiment.
Wow.
So yeah, those are hot air balloons. I don't know. I feel like I was missing something. It needs some more work.
Yeah.
Maybe in our free time we can figure out how to make that work better.
I'll let you know when I solve it.
Yay! All right, so I did ask you to bring a book today.
I did bring Let's see what book we've got.
And we have a fancy, super old-fashioned fancy book holder here. So let's just put it right in there. What? Harry Potter and the Sorcerer's Stone. That is one of the best books of all time. IMO. in my opinion. So, Harry Potter and the Sorcerer's Stone.
Yeah.
Tell me a little bit about it.
So I should say first off that I brought this one just because bringing all 7 is ridiculous. Maybe not. It would have been
We could have put them all out. It would have been fine.
I could have put them in clamps. But I wanted just to say that the series as a whole was very important to me as a kid. So I was given this one, and you can tell it's old and yellowed, and I was given this one when I was about 10, I think it was 10 or 11, and before any of the films had come out, and I started reading them obsessively. And I caught up because I was behind. JK Rowling had already put out, I think, 3 or 4 of them by the time I got this one. And the books were really important to me for a few reasons. One, it's really cool, right? But the most important thing to me was Hermione Granger's character. So I'm a woman. I identify as female, and I am in science. And before this point, I wasn't in science, but I was a smart kid, right? So I was the kid in class that was always raising my hand really annoyingly, doing these things, asking why a lot. And I didn't have a whole lot of friends when I was young because I was interested in books and doing these things, and I guess I was annoying probably. And reading about Hermione, I really saw myself in that character, and I didn't know that until many years later. I wasn't quite that visual as a child, but looking back on it, Hermione's character is a lot of the reason I think that I was able to just embrace the person that I wanted to be and just keep going, and keep raising my hand annoyingly in class and answering the questions. And it was okay that I was wanting to be smart and I wanted to study. Those things were okay.
That is so cool.
Yeah, and so
I believe that a lot of people feel that way.
I think so too. And so in this book, there's a quote that's actually a bit, it's polarizing to some people, but it's toward the end. Spoilers if you haven't read Harry Potter and the first one, so read it if you haven't. But spoiler, they're going through the different levels trying to get to the final chamber where the stone is, and there's all this drama, and Harry and Hermione begin to speak to each other, and you have to realize too that Harry's really Hermione's first friend that's seen her for what she is, and she says to him, "Ugh, books and cleverness, there are more important things in life," and she talks about bravery and loyalty, and that quote has really, really spoken to me because I do really care about getting the best grade on the test and spending my time in my books. I did really care about that, and almost too much sometimes. I really invested my identity in my grades and things, and that wasn't healthy, and I needed to learn how to get out of that. And so after having gone through all these years of school, I find that quote very, very important because I do grasp to my books and my cleverness, but I have to remind myself there are more important things too.
That's really important.
Yeah.
So are you a Ravenclaw?
Oh, I'm a Gryffindor.
You're a Gryffindor?
Yeah.
Okay. Well, I was just curious because
I'm very
Ravenclaw's
proud.
cleverness, right? Wit beyond all measure.
Yeah.
I'm a Ravenclaw. But no, that's really, really great. And, I think that, especially since you were 10, that's a really great age to begin Harry Potter, and especially for the kids that grew up with it as a similar age. Each book kind of grows with you as a person, and so it's very interesting to see how the characters change and the relationships develop and that sort of thing. So is there anything else other than Hermione that you took from the Harry Potter series that really helped you grow into the person that you are?
I would say investing in our relationships with the people around us, particularly as a scientist. Sometimes it's easy to hide in the books and the numbers and whatever, but throughout the series there are these characters that aren't even necessarily family, but they build these very important connections, and it teaches us how much we do need other people to help us be our best throughout life. And I think that's a really powerful lesson. And like you said, when you're kind of coming of age with the main characters in the series, I think that's part of their lesson too, is that they have to begin to lean on others. They probably could have defeated Voldemort in book 3 if they would have just asked for help, but they didn't. And so I think that that's a really important lesson that kind of goes through it.
Absolutely. So would you say in the world that we're in with all the technology and people kind of isolating themselves in their own, fields or their own passions. Do you think that relationships and networking are more important than ever?
Yeah.
Yeah.
And they're harder than ever, I think. So I'm an introverted person by nature, so I'm good in these settings because I don't have to speak to anybody except you individually, and that's okay. But if you put me in a networking or a mingling situation, I'm really uncomfortable because I would much rather sit with my book or look at my phone or do something that's less one-on-one. And so I have to work on that myself. And I think that continuing to build those skills and kind of hang on to them a little bit and realize the value that is in them is really important, and it's going to become ever more important.
As science and technology grows, especially a lot of scientists and people in the field of technology isolate themselves. And it's so important to make sure that you're developing relationships and getting to know each other because ideas, right? So in order to brainstorm ideas with each other and be able to make those connections, sometimes you'll realize something that you wouldn't have realized on your own.
Definitely. So the first C for clamps is collaborative. And so collaborative science, if we're talking about work, collaborative science isn't possible without stepping out from behind your screen a little bit. And usually that's kind of annoying. We all get grown, like, I could have gotten more work done if I didn't have to go to this meeting. But those things are really the things that push us to the next step.
That's awesome.
Yeah.
So where do you see meteorology being in like 10, 25 years?
Well, with the changes that we're seeing right now on the technology side, so our computers are becoming a lot more powerful. And when I talk about computers, I mean like the clusters and supercomputers we use to run our weather models to forecast. And so as they become more and more powerful, we're able to run more simulations, which is always great, but run them on finer and finer scales. And I think that we're entering kind of this paradigm in meteorology where our models are catching up with us, and they're going to maybe start getting things right, but we're not going to know why. And so I think that this is a new kind of avenue of science. The other side of that is big data and machine learning. That's becoming a huge thing in meteorology. And so I think in our field ourselves, there's still some fear. People really don't want to be replaced, by the computer.
Right.
But human forecasters will always be critical. That decision making will always be critical. Knowing who's living there, the demographics, how to communicate this information. We're a long way off from that being able to be replaced, but I think that we're at the precipice of something really exciting in our field.
Oh, yay, that's so exciting. Yeah. Well, thank you so much. This has been Elizabeth Smith. Let's give her a round of applause. So now I'm going to open up to the audience for questions. Does anybody have any questions for Elizabeth about the field of meteorology, perhaps her journey? Anything at all?
So if you weren't in meteorology, what do you think your career would be?
So when I was a kid, meteorology was always in the background, but there was a really long phase where I wanted to be a garbage truck driver. I'm really into large machines. I just like the way, and so watching the garbage truck like smash the trash is just like incredible to me. So something that works with that. So probably some sort of like engineering operation I would have been drawn to. The other thing I really like is cooking and meat. I really like meat. I like to cut up meat. That's kind of a creepy hobby, but I like that. I think it's interesting. So I think one of those directions. But yeah, maybe garbage truck driver.
That's very interesting. Thank you for that question.
Well, you spoke about climate change and then weather, which two things somewhat related though. So I'm interested from your field, as we see climate change and different things happening, how is that affecting the weather?
So it's a really good question. So there's a lot of questions out there about what the connection is between climate and weather. And now that we see these high impact weather events, so things like Hurricane Harvey last year and some of the other stuff that's been going on, wildfires, a lot of people really naturally start asking that question. If the climate's changing, are our weather events also changing? The answer I have to give you, unfortunately, is we don't know. So I'm not a climate scientist, but what I can tell you is that right now there's a lot of research in that area. But because any event, no matter how horrible or extreme it may be, it's a single event, it's really hard to tie it into these really long 100-year averages. However, if we continue to collect data, maybe once we get through 30 years or so, we can start to look and see if there's actually a pattern in the extreme events. But that's a very active, ongoing area of research, but it's an excellent question.
That is very interesting. Well, and you said that meteorology is a young science, which I was not aware of. What are some things you're noticing because of it being such a young science as you're progressing?
So I think one of the weirdest things about being in a young science is we go to the literature a lot, right? So when you do your experiment or your project or whatever, you have to put it into the context of what's been done. And if you go back only about 20, maybe 30 years, there is all this literature where there are these huge discoveries being made left and right all the time. Like, oh, we know why this happened, we know why that happened, we know why this happened. And it's actually a little bit discouraging if you let it be, because we've gotten far enough now into our science, it has matured enough that we're in incremental science. So most likely nothing that I'll do as a scientist is going to be this groundbreaking standalone discovery. And that's okay, that's true for most scientists, but because our science is so young, when you look back only 20 years and all of the discoveries were huge, it's kind of, but that's also really cool because it means there's still a lot of uncharted territory out there. So right now, a lot of the stuff we've discovered here in this part of the globe where we live, the mid-latitudes, we're now starting to explore what does that mean on the poles. There's people that are starting to explore how everything we've learned here on Earth might apply to the weather on Mars. These sorts of things. So there is a lot of uncharted territory out there, which is exciting too. But
well, and in 20 years, you'll still be in meteorology, so you'll be able to discover all sorts of things.
Yes.
Yay! Did we have any other questions?
So you were just talking about how just 20 years ago, all of these scientists were making all these amazing discoveries, and it's sort of hard to live up to some of those discoveries. How do you deal with something like imposter syndrome, where it seems like everyone else is doing amazing things and maybe you don't feel like you are?
So imposter syndrome is a really good topic. So in science, in other fields too, there's a lot of us, we kind of keep doing the thing and we never realize that we've actually accomplished the thing, right? And so then you're out there and you're surrounded by all these other amazing people doing the thing, and they look like they're really doing it well, and you have convinced yourself that you have somehow tricked everybody to let you in, and they're gonna find out that you don't know anything about what you're doing. I would say that the way that I try to deal with those sorts of feelings, which I have them all the time, the way that I try to deal with them is to really just laugh at my own mistakes. And that sounds funny, but if I don't let the silly stuff that I do or the mistakes that I make and sometimes the huge failures that I run into become something that I feel like I need to hide, then I can talk about them. And if I tell everybody how many disasters I do, then, well, obviously if I'm an imposter, they'll tell me at some point, hopefully. And so that's kind of funny advice, but my advice is to laugh at yourself. And whenever you start doing that in the workplace, a lot of times people kind of join in with you. So, you know, I explained to someone I was running this model forever, and then I realized that I had the whole thing turned the wrong way, and the ocean was hot, and nothing was real. And so I wasted a year. And then I laugh about it, because that makes people uncomfortable. I tell them I wasted a year of my life. And I laugh about it. And they're like, oh, you know, the other day I did this really silly thing. And then, you know, we can all kind of talk about how often we actually fail. Because we all fail. We fail a lot, but nobody gets invited onto these things to talk about failure most of the time. And so we get these images of people being super successful, that they only ever climb the mountain, climb the mountain, climb the mountain. We don't see how much they struggled to get there. So talk about your struggles, share them with others. Even if it makes you look silly, it'll make somebody else in the room feel a little bit better.
Right, well, and it makes you more relatable.
Yes.
Because nobody wants to see a superhero with no weakness. They only relate to the superheroes who have something super about them, but also have something relatable and human, or failure or a weakness is a learning experience.
It is.
And so any failures that you've had, any challenges that you face, you're going to learn something from that and be able to grow. Because without those, we don't grow.
We'd be really boring people if we never failed.
Yay! Failure! But really, that's all science is, right? You're making experiences, you're making mistakes in those experiences, and then you're learning from them, and usually we stumble across something that'll help us in the future.
Science is professional failure in a lot of ways.
Ooh, I like that.
Yeah.
Science is professional failure.
Yeah.
Excellent. I love it. Well, thank you so much, Elizabeth. Everybody, thank you so much for your questions. This has been Yes!